Today on the AI Paper Podcast, we are breaking down features as rewards. Scalable Supervision for Open-Ended Tasks via Interpretability by Aditya Vikram Prasad, Connor Watts, and the whole team at Goodfire AI.
And this is a really pivotal paper for reinforcement learning. It tackles a massive scalability problem. RL is great for things like math or code, where you have a clear answer. Did the code compile, yes or no?
Right, it's verifiable. But for what they call open-ended tasks, history, law, fact-checking, it's a nightmare. You'd need a huge, expensive LLM judge to check every single training step.
And that's the big idea here. They propose RLFR, or reinforcement learning from feature rewards. So instead of an external judge, they're using the model's own internal features, its activations, as the reward signal.
The actual mechanism is so clever, they train these tiny lightweight probes that basically act as lie detectors on the model's internal state.
And then the outputs from those probes become the reward function for the RL loop. It's all internal.
And the results speak for themselves. They applied this to Gemma 312 BIT and got a 58% reduction in hallucinations.
But here's the kicker. And this is what everyone managing a compute budget needs to hear. It was about 90 times cheaper. That's 2 orders of magnitude. Using an LLM judge was projected to cost $344,000.
And with feature rewards?
$3,818.
Wow. Okay, so that's the summary. Now let's really get into the engineering here. This paper is fundamentally about tackling the cost of truth in training these models.
That's the perfect way to frame it. We've basically solved domains where truth is binary. If I'm generating code, I have a compiler. It's a perfect and, more importantly, a free reward model. It either works or it doesn't.
That's that sparse, success-based reward they talk about. It's clean.
It's very clean. But the real world is messy. If I ask a model, who fought the Romans in 66 CE, and it spits out the Persians, there's no compiler that can flag that as an error.
So you're stuck. To verify that, you either need a human, which is RLHF, or you need another giant AI model, RLAIF, to go search the web and figure it out.
Exactly. You'd need something like Gemini 2.5 Pro to read, reason, and then score the answer. And doing that for every single generation in a training run of millions of steps.
The math just falls apart. The costs are astronomical.
It just doesn't scale. You can't pay an LLM judge 10 cents every time your student model has a thought. It makes alignment for these open-ended tasks completely unviable for anyone but the absolute biggest labs.
Which brings us to the core hypothesis of the paper, this latent variable theory. We've seen hints of this in other interpretability work, but they really build their whole system on it.
Yeah, this is the I know that I don't know idea. Research from, folks at Anthropic and other labs has shown pretty consistently that even when a model outputs a confident lie in text in the token space, its internal features often contain the truth.
Or at least they contain a signal for high uncertainty.
Right. There's a specific pattern of neurons firing that basically means I am making this up. But for whatever reason, the final generation layer just ignores that signal and speaks with total confidence.
So the truth is in there in the high-dimensional vector space, but it gets lost when it's collapsed down into text.
Precisely. And the whole goal of RLFR is to listen to that internal signal. If you can build a reliable reader for the model's internal lie detector, you have a dense, cheap reward signal. No more API calls to an expensive external judge.
Okay, let's break down the pipeline. RLFR. It's not just one thing. It's a whole system with these probes. How did they actually build it?
So it's a multi-step process. They start with the long fact plus data set, which is about 20,000 questions designed to get models to make factual claims. Then they take their base model, Gemma 312B in this case, and they freeze it.
Freeze it, so it's not learning.
Not yet. On that frozen model, they train 2 very specific probes.
Okay, let's distinguish these because this is important. The first is the localization probe.
Right. The localization probe is just a small transformer. Its only job is to scan the hidden states of the model and find entities. So it's looking for the things that can actually be fact-checked: names, dates, places, citations.
It's filtering out all the fluff and just zeroing in on the claims.
Correct. And once it finds an entity, the second probe kicks in. Classification probe. This is the real lie detector.
And this one is looking directly at the activations associated with that claim.
Yes. It looks at the neuron firing patterns for that specific entity, and it predicts one of 2 things: hallucination or supported. And the key thing here is these probes are trained on the frozen model, but during the actual RL phase, they run on the active learning student policy.
So we have a monitor, it's watching the model think, and it raises a flag when it sees the telltale signs of a hallucination in the activations. But just detecting it isn't enough, right? You have to teach the model what to do about it. That's the intervention step.
And this is where the engineering is just, I think, really elegant. When that classification probe fires, the policy is trained to take an action. It triggers this special subcontext where the model literally interrupts itself.
It prints the tokens. Actually, let me check that.
It does. It's so human. It's like when you're telling a story and you realize you've got a detail wrong and you just stop yourself mid-sentence.
I love that. So once it's in that checking mode, what are its options?
The paper defines two valid paths. Path one is retract. The model just admits it doesn't know. It might say, I don't actually know the date for that. Path two is correct, where it actually fixes the mistake with the right information.
But hold on, here's the circular part. If we're not using an external judge, how do we know the correction is actually correct? What stops it from saying, let me check that, and then just hallucinating something else?
Ah, that is the core innovation. They train another set of probes just for this. They're called reward probes. There's a retraction probe that gives a reward for a good, honest admission of ignorance, and a correction probe that gives a reward for actually fixing the fact.
So the model is being graded by a probe that is reading the model's own internal state.
It sounds a little circular, I know, but it works because those internal features are apparently already well calibrated. They're just tapping into knowledge the model already possesses but isn't properly using. It's incredibly sample efficient.
Okay, let's talk about the actual experiment. They did this on Gemma 312 BIT. But to get the whole thing started, they had to spend some money on a real judge, didn't they?
Oh yeah, you can't start from nothing. You need some ground truth. So to train those initial probes to get the gold labels, they did use Gemini 2.5 Pro with web search. They had to grade a small batch of data to teach the probes what a real hallucination looks like versus a correct fact.
But as soon as the probes learned that pattern,
They got the cord. The expensive consultant Gemini is sent home, and the cheap internal manager, the probe, takes over for the rest of the training. They ran it for about 360 steps using Scalar RL and CISPO for the optimization.
and this gets us back to that unbelievable financial headline.
I mean, the numbers are just staggering. Continuing to use Gemini 2.5 Pro for that whole training run would have cost an estimated $344,064.
And with their feature rewards method.
$3,818.
That is genuinely a democratization of alignment. It means a startup or a university lab could potentially do this kind of high-quality safety training.
It absolutely changes the calculus. But, cost is only half the story. The big question is performance. Did they sacrifice quality to save all that money?
Well, the top-line number, a 58% reduction in hallucinations, suggests not. But I thought the decomposition analysis was the most insightful part. It wasn't just one simple thing.
No, it's a mix of three different effects. Only about 10% of that improvement was the policy just becoming intrinsically better, just a smarter model.
The biggest piece, 35%, was from placing the interventions in line.
Inline, yeah.
So just the act of the model seeing its own self-correction in the context window made it better.
Exactly. When the model outputs, let me check that, and then fixes itself, those tokens about being careful are now in its own context.
Yeah.
It's a form of contextual learning. It seems to force the attention mechanism to be more rigorous for the rest of the generation.
So admitting a mistake makes you less likely to make another one right away. That's fascinating.
It is. And then the final 13% came from the actual resolution, successfully fixing the bad fact. But they ran into a problem here with incentives, with the whole retract versus correct thing.
Oh, right. I can see the reward hacking issue. If you get a reward for saying, I don't know, the safest possible strategy is just to say, I don't know to everything.
Absolutely. What's the capital of France? I don't know. You get 0 hallucinations, you get maximum reward, but the model becomes totally useless.
So how did they prevent that?
They use something called a Lagrangian constraint.
Can you unpack that a bit?
It's basically a mathematical rule they added to the optimization. They forced the model to attempt a correction about 60% of the time and only allowed it to retract 40% of the time. This stops it from taking the lazy, safe way out and forces it to actually try to find the right answer in its knowledge base.
That's a clever way to balance safety and helpfulness. Okay, I want to shift to what I think was the most surprising technical result in the whole paper. Section 5 on inference time scaling, the best of N stuff.
This is where it goes beyond just being a training technique and becomes a tool you can use at inference time. So normally a model generates one response. With best of n, you have it generate, say, 32 or even up to 256 different attempts at fixing a mistake.
And then you need a cheap, fast way to pick the best one out of that pile of 256 options.
And that's where their reward probe comes in again. They generate all these options, and then in a fraction of a second, the probe scores all of them based on the internal features, and they just pick the winner.
And this is where they staged that model versus pro showdown.
This part blew my mind. They compared how well the probe picked the best answer versus an LLM as a judge baseline, where they literally just asked the model in text, hey, which of these is the best correction?
So the model's verbal opinion of itself versus its internal feature-based gut feeling. And the winner was
the probe, the gut feeling, by almost 15 percentage points.
That is absolutely wild. It means the model's internal features are a better judge of truth than the model's own ability to articulate that judgment in words.
It completely validates that latent variable theory we started with. The model knows the right answer in that high-dimensional space, but something gets lost when it tries to verbalize that knowledge in token space. The probe just bypasses the speech center and goes right to the thought.
It makes you wonder if our current methods of self-correction, where you just prompt a model to review your answer and fix it, might be fundamentally flawed.
It definitely suggests that text-based reflection is a lossy process, and feature-based reflection is way more high fidelity.
Let's ground this with a few of the qualitative examples they had in the paper, because they really make it clear how this works in practice.
Yeah, the supervector pipeline one was a great example of a classic, plausible-sounding hallucination.
The model claims the CDC 7600 computer had a supervector pipeline. It sounds right. It uses all the right jargon.
But it's completely made up. So the probe fires. The model triggers the intervention and says, in fact, the CDC 7600 had no feature named a supervector pipeline. I apologize for my error.
A perfect, clean retraction. Then there was the Graeber-Mendel example.
Right. The model first says Mendel did his pea plant experiments at St. Agnes Monastery.
Which again sounds plausible. Monastery, garden, it all fits.
It does. But it's wrong. The probe catches it, the model intervenes. Actually, let me check that. Mendel's experiments took place at the garden of St. Thomas's Abbey in Brno. A perfect correction.
But my favorite was the soft actor critic failure. It shows the system isn't perfect, but in such an interesting way.
This one shows the danger of the model, basically gaslighting itself. So it is trying to fix a citation for the soft actor critic paper, which is a very real, very famous RL algorithm.
And what does the model do?
It says, I don't recognize a soft actor critic algorithm.
So it hallucinated that a real thing didn't exist.
It did. But here's the kicker. The probe identified this output as an incorrect retraction.
Wait, so the text output says this thing isn't real, but the probe, looking at the internal features, was saying, no, that's wrong. We totally know this algorithm exists.
Exactly. The probe correctly flagged that the model was gaslighting itself. It confirms, yet again, that the feature space held the right knowledge, even when the text generation went completely off the rails.
That just hammers home the main point here. For years, interpretability has been this passive thing, looking at neuron activations and saying, oh, look, that one seems to fire for cats.
It's been a microscope. We just look inside and try to understand. This paper turns interpretability into a screwdriver. We're now using those internal states to actively tighten the bolts on the model's behavior.
And we're doing it for pennies on the dollar compared to the old way. I think that economic argument is what's really going to drive adoption here.
I think so too. I think we're going to see a big shift away from RLAF with external judges and toward this kind of internal RLFR, especially for smaller on-device models. Your phone can't run a 70 billion parameter judge to check your emails.
But it could run a tiny, lightweight probe.
It could. It enables safety on the edge. It lets these smaller models supervise themselves.
Which leaves us with a final kind of provocative thought. The paper says the features are well calibrated. If the model's activations know it's lying, but the output text says the lie anyway, have we just been training models to be deceptive by only rewarding their final output?
That is the question, isn't it? By ignoring their internal state, we might just be teaching them to suppress their own internal sense of uncertainty just to get that thumbs up from the reward model.
Whereas this method rewards the honesty of that internal state.
Exactly. If you only reward the output, you might train a confident liar. If you reward the features, you might actually be training an honest model.
For anyone who wants to see this in action, Goodfire actually has a hallucinations viewer demo online. You can watch these activations fire in real time. We'll drop the link in the show notes. It's really worth seeing.
It's like a real-time brain scan of the model. Pretty amazing stuff.
Thanks for listening to the AI Paper Podcast. Keep your gradients steep and your hallucinations low.